Well, hello everybody. So, today we are going to the third topic of this particular lecture series on adiabatic two-phase flow and flow boiling in microchannels. Now, yesterday what we did, rather in the last class what we did was we tried to find out the importance of microchannels, why it is so very much used and what are the typical flow patterns that we had encountered there. Now, before we do anything else, the first thing which I think we should be discussing is how do we define microchannels, or in other words, under what conditions do we say that this particular this falls in the criteria of microchannels and this falls in the criteria of millichannels and so on. Okay. Now, let me tell you, there has been no definite criteria, rather there have been a large number of controversies regarding the classification. Now, the first thing which was done was that the classification was done based on simply the diameter for circular pipes and the hydraulic diameter for non-circular pipes. Now, this was the way which engineers very frequently used to just define these things. It was thought that, well, anything which is in the millimeter scale is a millichannel, anything which is in the less than that, it is a microchannel, and then something conventional pipes, they are your ordinary pipes, they refer to the macro system and so on. And so, therefore, the initial classification was based on hydraulic diameter. You can see that these particular classifications, they have been done both on the basis of compact heat exchangers as well as for conventional channels. Now, if you look into them, you will find that, well, some particular person he has defined the mesoscale for heat exchangers between 100 to 100 micrometer to 1 millimeter, while the same thing has been defined by someone else based on 200 micrometer to 3 millimeters. So, we find that there is quite an amount of disagreement between these particular and there is no exact definition or proven criterion available for distinguishing the micro domain, the macro domain and the transition between the two. Knowing fully well that the transition does not occur abruptly at one particular dimension, I cannot say that, well, above this it was a macro, below this it is a micro. So, therefore, there is a range over which the characteristics of the micro domain gradually gets transitioned to that of the micro domain. Now, the initial attempts were just to define it in terms of hydraulic diameter. Okay. Now, in this particular situation, what people actually wanted to do was they just wanted to differentiate the studies which have already been reported in macro systems and the studies which were currently being reported in reduced dimensions and which were not tallying with the studies or the information already available. So, this was the initial criteria based on which the macro and the micro scales had been differentiated, and the basic thing, as I have already told, that it was just to differentiate the studies which have been performed in conventional pipes and the studies which are being reported or were being reported in reduced scale, and they were not agreeing to the information already available. In due course, people found that just the physical dimension is not sufficient, and there should be some sort of a proper coupling between the physical dimensions as well as the local flow variables and the physical properties of the fluid. So, therefore, based on this, people, or rather several researchers, they had tried to combine the local flow variables and the physical properties of the fluid, and it was backed by numerous flow observations and extensive databases, and along with that there were accurate methods to predict the hydrodynamic and thermal performance both in the macro domain, in the micro range and also in the intermediate domain, which was commonly referred to as the mesoscale or the millichannels. Accordingly, we find that several particular criteria of definition came up, and as a consequence of which several dimensionless parameters had been proposed. Now, we find, if we look at this particular presentation, we find that the the definitions which were proposed, they were based on several numbers. For example, the confinement number, the Yordwas number, the the capillary length, and so on and so forth. Now, at this particular stage, I would also like to mention one thing, that when the classification was based on hydraulic diameter, what people found was they were just defining in terms of the physical dimension, but then they realized that it is not the physical dimension which is sufficient. For example, suppose we are working at a very high pressure. When we work at a high pressure, then and suppose boiling is occurring and bubbles are generated. Now, at this particular high pressure, the bubbles generated will be very, very small, almost of micron size, and under that circumstance a 1 millimeter channel can serve as a macro domain. On the contrary, in the same particular tube, if we are working under sub-atmospheric conditions, then in that case it would behave as in the micro scale. So, therefore, from here people came to know that simply defining micro, macro and meso in terms of physical dimensions are not sufficient, and then they started defining several dimensionless parameters. The different dimensionless parameters which were used, first was known as the confinement number, where this basically what it does is, it is defined as 1 by d root over of sigma by g into rho L minus rho V. It is very evident that it gives you a balance between the surface tension forces and the buoyancy forces. Now, this number, it is based on the confined growth of a bubble in small channels. This was based on confined growth of bubble in small channels, where the effect of surface tension was important, where surface tension effect. So, this was primarily practiced for flow boiling situations, where we found that normally what happens in a large channel, a bubble it starts, or rather it starts forming at the nucleation site, and then it gradually becomes larger and larger. At some particular critical diameter, it detaches from the site and then starts rising due to buoyancy, and when there is a flow system, it is also pushed faster due to the flow system, and therefore, the detachment occurs at a faster rate. Now, in small channels, what happens, when the bubble starts forming at the nucleation site, before it can detach from the site, it gets confined by the upper wall, as a result of which it cannot escape from the nucleation site, and it starts becoming larger and larger. Now, this is definitely, it depends upon the surface forces, or it depends upon the surface tension, or rather in other words, the role of surface tension must be quite important in deciding the maximum bubble radius. We know that the maximum bubble radius at detachment, it will decrease at the expense of the gradual suppression of the gravity force with channel diameter. So, as the channel diameter decreases, this maximum bubble diameter also decreases due to a decreased effect of gravity forces. So, based on this, we find several researchers, they have proposed a criteria. For example, one particular group of researchers, Q and Cornwell, they suggested that this confinement number should be less than 0.5 for macro domain and greater than 0.5 for micro domain. The criteria or the observation was that there should be an existence of confined bubble flow. In other words, the bubble should be confined between the two walls and flow as elongated isolated bubbles. Apart from this, there was another particular important dimensionless group which was suggested, in order to decide the criteria for microchannels. That is a balance between, that is also a balance between surface tension forces and buoyancy forces. This particular number is often defined as Yodworth's number, or a reciprocal of it is defined as the Bond number. Different researchers have defined it in different particular ways, and some have defined it as a Yodworth's number, some have defined it as a Bond number. This actually I have written the reciprocal of it. This is often defined as G into rho L minus rho G into D square by 8 sigma. And this has been defined, I believe, by your by Ullmann and Browner. They have defined it, and so it shows, and they have suggested that Yod was close to 0.2, which corresponds to confinement number close to 0.79, is going to decide the criteria between macro and micro channels. On the other hand, this Browner and Maron, they had a slightly different definition of this Yodworth number, and they proposed a slightly different criteria for this. Now, the criteria which was proposed by this Browner and Maron, it read something of this sort. The criteria which it had a 4 pi square in it, as a result of which the definition was slightly different in this particular case. Now, we find that the criteria, they have defined some particular criteria, and that was correlated to some particular physical observation. What were the physical observations? First thing is, maybe stratification is suppressed. All of us, we know that when stratification gets suppressed, it is the termination of macro scale. The other criteria which was suggested was onset of asymmetric phase distribution in horizontal pipes. So, usually what was thought was that moment stratification gets suppressed, it is the termination of macro scale, and when the phase distribution becomes symmetric, this is defined as either symmetric plug flow, or maybe in annular flow, the film in the upper part and lower part of the channel, they are more or less symmetric. By any one of these criteria, it is decided that the onset of symmetric flow marks the inception of microchannel, and the range from where the stratification is suppressed and symmetric flow is starting, this particular range is defined as the mesoscale or the mini scale. It will be interesting if you observe the different criteria which people have selected, and that will explain that why there are so much of discrepancies in the criterion for the criterion of defining a microchannel. Say for example, one particular researcher group, Q and Cornwell, they decided on the basis of your confinement number, which marks the existence of confined bubble flow. Then there was another group, Suo and Griffith. What they did, they defined it in terms of Yodworth number, which suggested, or their relevant observation was negligible buoyancy effect on Taylor bubble. So, when in a, just as I was telling, the onset of symmetric flow distribution. Then another group, they did a very extensive review of the characteristics of two phase flow, and they suggested the criteria on the basis of 6 dimensionless groups. They had chosen Bond number, the superficial Weber number of the two phases. As I had already mentioned, Bond number gives you a ratio of the buoyancy to surface tension forces. Weber numbers of the two phases, they give us the ratio of inertial to surface tension forces, and both of these are based on inlet input conditions. Then they had also defined Reynolds number, which as we all know is the ratio of inertial to in fact, this is not properly written, it should have been mu. So, therefore, they are the ratio of inertial to viscous forces, and the capillary number, which is the ratio of viscous to surface forces. So, based on these numbers, what they did, they decided the criteria on the basis of bond number, and then they fixed all the other numbers to decide the domain of microchannel flow. Here again we find that mostly people have used bond number and Yordwas number, and again just I was telling, there was another group who had decided upon the 6 groups including superficial vapor and liquid velocities to decide upon the criteria. Then there was another group, what they did was they defined 2 diameters. One was the threshold diameter, the other was a critical diameter. Now, based on these 2 definitions of threshold diameter and critical diameter, they defined the threshold diameter as 1.75 lambda, where this lambda, it is the capillary length which I have already defined earlier. This is given as sigma by g into rho L minus rho g whole to the power half. Now, this is known as the capillary length or the capillary constant, whatever you wish you can call it. So, what this particular Lee and Wang group did was they defined 2 diameters. One was defined as the threshold diameter, which was 1.75 times lambda. The other was defined as a critical diameter, which was 0.224 lambda. And what they did, they based on these 2 diameters, they found out that for certain cases, for example, when the conduit dimension or the equivalent diameter was less than equal to the critical diameter, they found that gravity effects were insignificant, and annular, elongated bubble and bubbly flow regimes, everything was symmetric. Then again they found that when the diameter was in the range of critical and threshold diameter, gravity effects were visible, it is true, but the surface tension effects were more dominant, as a result of which the stratification was not there, but non-symmetric effects on annular, elongated bubble and bubbly flow regimes were quite evident. And again, when the diameters was greater than equal to the threshold diameter, the effect of surface tension was small with respect to gravity, and they found out that the condensation flow regimes were similar to those in microchannels. Now, one thing I just forgot to mention, I think that this particular researcher group, they determined the effect of conduit size on 2-phase flow regimes for in-tube condensation studies in horizontal tubes. So, their postulations were based on condensation studies in horizontal pipes, and during such studies they tried to understand the effect of gravity by investigating the transition from asymmetric to symmetric flows, and they did it based on the Young-Laplace equation, where the capillary constant was defined and 2 dimensions were defined based on the capillary constant, and then the entire range of your macro domain, the micro domain and the mesoscale was defined very well by them. Well, I should say this is possibly the first proposition for macro scale, or rather macro to micro scale differentiation, which could be applicable to both adiabatic as well as flow boiling or flow condensation systems. Previously, most of the studies, they were confined either to flow boiling, where the confinement number etc. was important, or to adiabatic conditions, where Yordwas number was important. So, more or less based on what we find is surface tension is important here, and the balance of surface tension with buoyancy or maybe the confinement of how it affects the confinement of the bubble, these things were taken as the criteria, and the observations which were used to relate this particular transition, or rather to correlate this particular transition, was, as I have already mentioned, suppression of stratified flow and onset of symmetric flow distribution in bubbly, plug and annular flow regimes. Well, so this was primarily for adiabatic flow conditions. Now, if we observe that several criteria have been suggested based on flow boiling experiments. Now, in nucleate pool boiling experiments, what we have seen that in microscale level there is no stratification. Why? Because the bubbles, they get formed at the nucleation site, as I have already mentioned. For a macro system, what happens? These bubbles start growing at a particular critical diameter, or where the forces acting on the bubble are more or less balanced. The bubble gets detached, due to buoyancy it starts rising, and when there is a flow occurring, then the flow also assists in its detachment from the nucleation site. Now, in the micro scale we find that when these bubbles, they get accumulated on the top, naturally they coalesce and form the stratified flow domain. Now, as we all know that this stratification does not occur in the micro scale situation. So, therefore, the first researchers who adopted this concept were Jacobi and Thome. What they chose the bubble departure diameter as the determining criteria for macro to micro transition. This diameter, they postulated, was the diameter of the growing bubble when it reached or it attained the size of the internal diameter of the tube before detachment. So, therefore, while it was detached and growing, it touched the upper wall, its dimension became, or its diameter became comparable with the diameter of the conduit channel, and naturally after that there was no question of detachment. It could not rise in the vertical direction, it got elongated in the axial direction. So, naturally there was no stratification. So, this particular criterion was first proposed by Jacobi and Thome as the transition from macro to micro scale for flow boiling experiments. And subsequently we find that several expressions have been proposed for the bubble departure diameter. They have been expressed in terms of the contact angle. Some researchers, they have expressed it in terms of the saturation temperature of the fluid, the liquid specific heat and latent heat, but they did not include the contact angle in their expressions. And here also we find that in order to define the departure diameter, another dimensionless parameter has been defined. We will be discussing these dimensionless parameters after a few lectures when we discuss the importance of dimensionless groups in adiabatic two-phase flows, and then later on we will be discussing the same for flow boiling. So, here we find it adds the influence of wall superheat, liquid Prandtl number, liquid dynamic viscosity, yet contact angle was not included here. Same way, based on this particular dimensionless group K1, a different expression of bubble departure diameter was proposed, and yet in this particular this I have already discussed that in boiling as well as condensation, a threshold and a critical diameter was discussed and so on. And interestingly, before I proceed, I would like to show you that based on the dimensionless numbers, when the critical diameter was defined, we find that for air water we have one set of critical diameter, for kerosene water they give another set of critical diameter, and even for air water and kerosene water systems also we find that the dimensions, they are remarkably different. So, from here we can very well get an idea regarding the discrepancies which are already available in the definition of macro to micro scale, and this also suggests that there is a necessity for further studies in this particular field. Now, while we were discussing these things, something became very evident, that this particular transition, as you have already understood, This does not occur abruptly. There is a range of dimensions which we call as mesoscale where this particular transition occurs. Now, this mesoscale, it is very interesting to us primarily for two reasons. Firstly, in this particular scale, both surface tension and gravity becomes important. What do we find? We find that in the macro scale, gravity was important, inertia was important, viscous is important under certain circumstances when we deal with viscous liquids. In the micro scale, surface tension becomes very important, gravity is suppressed. But in the mesoscale, we find that both surface tension and gravity are important, with a decreasing importance of gravity and increasing importance of surface tension with decrease of conduit dimension. So, naturally the physics of this particular scale is unique and definitely it should be very different and interesting. So, in the course of our lectures, while dealing with flow in microchannels, we will also be touching upon or discussing flow in mini channels or in the mesoscale. In fact, I have already done it when I was discussing the flow patterns in the previous class. There are also several other advantages in this mesoscale, due to which they are quite they have been the focus of research recently. The advantages being easy to fabricate. Naturally, when we discussed microchannels, you will be remembering the first thing which I told you, that they are expensive and it is difficult to fabricate. So, in that way mesoscale is better. Then rapid prototyping is easier. The problems of channel getting choked, that does not happen. On the other hand, high specific heat transfer area is also available in this particular channel. Just to show you the uniqueness of millichannels, I would just show you the flow patterns in a 2.5 and a 8 millimeter tubes. They have been recorded in the multiphase flow laboratory of the chemical engineering department. You can see that just for such a small difference, in what way the flow patterns have changed. You can observe the bubbly flow pattern here, the increased density and size of bubbles here, the regular shaped Taylor bubbles for 2.5 and the irregular shaped Taylor bubbles for 8 millimeters. And you can also observe the smooth interface in the falling film flow for 2.5 and the wavy interface in this particular case. So, therefore, this shows the effect of tube diameter in the milliscale. Now, if we go to observe the effect of inclination, we find it is true that in the miniscale there is no effect of orientation, that is true. Stratification is suppressed, that is also true. There is a predominance of slug flow, that is also true. But if you observe little more minutely and if you try to observe the range of flow pattern, then we find something very interesting. In order to discuss this, what we did, we tried to plot the range of slug flow for these three orientations in a two-dimensional plot with the liquid and the gas superficial the water and the tolling superficial velocities as the two axes. And very interestingly, we find here that the downflow, in the downflow orientation you can find, this shows the downflow orientation, slug flow range is the maximum and it is the minimum for the horizontal orientation. This shows the horizontal, the black line shows the downflow and the points show the upflow orientation. So, we find that although stratification is suppressed here, the flow patterns appear to be more or less similar, or the morphology appears to be more or less similar, with slug flow predominantly and annular flow also. Yet we find that there is an effect of inclination and this adds a new dimension to the study of two-phase flow in reduced dimensions. So, with this I would like to conclude this lecture session stating that we will be continuing our discussions on mini and micro channels in our subsequent lectures. Thank you very much.